I would assume, yeah. That's what they're gonna do over the summer. Okay, really quickly. I didn't get everybody's. So I passed out everyone's. I'm gonna have to email. That's what I was actually about to talk about. The only other ones I have are Sanaya's, Treyana's, and Miracles. So I don't know where all the other juniors. I will go and talk to Miss Jemison and try to find out what happened to the rest of them, and have them tomorrow or Friday. The ACT, the math, or your ACT scores. Yes, ma'am.
Shania and Naya are at high school right now. They're doing like either one welcome or they're there for children.
Gotcha. So they'll be back at some point.
Yes, sir.
Cool. Thank you. That's good to know.
Late afternoon, but it takes 2 hours to get to Oxford. 2.5 hours.
So what I will say, because I saw there's a group leaving at 9 or so. We still are planning, or I'm not still planning. We are having a test on Friday. I'll still be teaching to review and prepare for that with an understanding
We
check.
don't know there's a group leaving at 9.
I saw a Facebook message that like carpool thing at 9. I don't know. The teacher posted about it. I don't know. That's just what I read on Facebook.
We heard that they're not doing a bus this year because of how late the games are. So we'll probably get home around like 2:30. It's not 2:30 more. It's like 12 o'clock in the morning as is. So that's on a school night. So I'm not going tomorrow for that reason.
Okay.
So Friday I'm gonna go, but I'm not gonna leave it like that early. I'm gonna leave it like 11:30.
Okay. And so we'll figure it out. I will say, like, for my softball players, if we have to take the test next week, we can do that. But the test is Friday, so I can grade them and figure out who's exempt. So we may have to play around with it. Understand check tomorrow. I planned for it today, but I would rather do the understand check tomorrow, go over it immediately, give you that feedback, make scans, and hand it back. All right, so let's look at this bell ringer as a review once again, to help us prepare for, one, just remembering things in general, but also for our final that some of us will have to take. So what function we have here, I named it k of x. So k of x equals 3 times negative x plus 3 times x minus 4 times x squared minus 4. So I see the fact that several of us are saying concave up. I see 3 zeros. I see 3 zeros concave down. I see concave up. I see cubic function. And guys, that means we need to pay attention and look at this again. It's not a cubic function. Why not? Because that x squared. This piece right here is what type of function? Just this piece, if I were to graph this, what would it look like? It'd be linear, right? Y equals mx plus b. So how many zeros is that linear going to have? 1. The next piece there is what type of function?
Mr. King.
Yes, ma'am.
Do you need me to go check it? I'll talk to Mr. King about make my example
Gotcha.
on a different day.
Right here, this piece is linear as well, so how many zeros does it have? 1. So 1 0, 1 0. But look at that one again. What type of function is x squared minus 4? So how many zeros would that quadratic have? So how many zeros are there?
3.
Or sorry, hold on,
It's 4?
It's 4 zeros. 1, 2, 3, 4. And we're going to look at this in a little bit more detail in a second, but I do need y'all to notice, like, that we cannot just say, hey, there's 3 factors, so there's 3 zeros. I purposely created this problem because I thought this would catch some of us, but it caught a lot more of us than I expected. So please learn from this, right? It's okay to make mistakes. It's not okay to stay in those mistakes. We want to grow. We want to learn. We want to become better tomorrow than we were today. So we have a total of 4 zeros here. I will point this out for, I had 3 students, I think, yesterday do the retest. And once again, when I asked the question, what are the zeros, they told me, oh, there's 3 zeros. That's not what I'm asking if I ask you what are the zeros. If I'm asking you what are the zeros, what are you supposed to do?
You have to write it down.
So find the Zeros, there we go. We need to actually, oh, sorry to erase that, that's my bad. We actually got to find those zeros. So how do I do that, Jayla? How do I find zeros of a function?
You say, what they call it, you equal all those to zero.
So you said each starts with an F.
Factor.
Factor. Because what do we do with factors? We multiply, right? That's why they're called factors. We're multiplying there. Now, more plainly, even before that, like if I'm trying to find a zero ever, because that only works in factored form. If I'm ever trying to find a zero, what do? Desiree, why do we call it a zero? Come on, where's that term zero coming from? Something's got to be a zero, right? What would have to be zero because we're calling it a zero? Say it again. So remember, Desiree, everybody else, the y value or the output is zero. That's why we call it a zero. The output is a zero. That's why, what's another word for a zero, Marshall?
Zero.
Well, what's another word for a zero? Think about the statement we just made. Make sure we're engaged. The y value is zero. So what's another term for that zero? It's what we would see maybe on the graph.
The y.
Very close. But the y value is zero. Where would I see a y value of zero on this graph?
Y.
So if I look at this point, that's 0, 2. That's not a y value of 0. That's an x value of 0. I mean, in the center right here, so that would have a y value of 0. Does anybody see another point up here that might have a y value of 0? So what do we call, what's another word for a 0? Well, it's on the x-axis, so it's called an x-intercept. Guys, we gotta remember, math is a study of patterns and relationships. This is a relationship. Zeros are also x-intercepts because the y value is 0. And so when I look at this, so Jaylee, earlier you said set each factor equal to 0, right? Why should it make sense, looking at this equation, that I would set each factor equal to 0? What have we learned that tells us to set each factor equal to 0? Zero product property. The only way to get a product of 0 is what, Miracle? What's the only way to get a product of 0? Well, the zero product property is what we get as a result, right? But what does that really mean? It means that we have to be what? Kind of close. You have a lot of the right ideas around there. Jacoby, do you remember the language I always used with it to get that zero product property? What has to be true? Yes, the equation does have to equal to 0, but how? What happens from that? Sorry, that was from your data. Let me ask this, Miracle. What would I have to multiply by to get a product of 0? Right.
What are the factors equal here?
Right. The only way that I get a product of 0 is if I multiply by a 0. So we set each factor equal to 0. What happened to the what? Good question. I could set that 3 equal to 0, but does 3 equal 0?
No, not really.
So that doesn't give me a solution.
I know that I'm saying, like, what heck? Why you just keep working?
Yeah, I mean, it would just say right there, but notice it's not going to help me find a 0 because there's no variable. I know. But I know, but Elijah, I was just illustrating, like, we could set every factor equal to 0, but when I set this equal to 0, it doesn't give me a solution. That's all I'm saying. Okay? So, what would I now use to solve each of these equations? Well, I already used the zero product property to set each factor equal to 0. So use those inverses. Negative x is equal to negative 3, so what does x have to equal? Okay, negative x is equal to a negative 3, x has to equal positive 3. If x minus 4 is equal to 0, X would have to equal a positive 4. We add 4 to both sides. Now this is the one where we have to pay attention. Remember, we said we should get how many zeros out of this? No, this one, sorry, this one right here. Yes, you're right, 4 overall, but this one right here? So very cool. Remember, what degree is this? X squared, so it's degree 2. So I need to get 2 zeros. So Phoebe, what do I need to do to solve this equation? Okay, so remember, I need everybody to pay attention to this. If I'm using inverses, what's the first thing happening to x? It's being squared, then subtracting 4. So the last operation is the first one I undo. Now what? So what does x equal? Remember, when you take that square root, we need both a positive and a negative. So how many zeros did we get here? So how many zeros do I have? 4 total, which matches the fact that we said there were going to be 4 zeros. Yes, sir. What did I miss?
You didn't put the 0.
What?
From where? -4 + 4.
Oh, thank you. I told you guys to write that 0 on both those. Thank you for catching that. All right. Now, 2 things I do want to point out. We want to pay attention to this detail. Yes, ma'am. Do what again? Yeah, you can go to the office. So, so first off, we have 4 zeros here. We would want to pay attention to that. Again, what degree would that be? 4th degree. Shania, do you remember how many extrema this k of x could have?
I don't even remember the extreme.
Does anybody, can anyone clarify what we mean by extrema? Those are the terms, right? So, the number
Oh,
of...
so it'd be 2.
Not 5 terms. So this is just a random switch. This is not for that. Sorry. Remember,
You're not going to believe me.
well, what degree is it?
4.
Degree 4.
4 zeros.
So we got 4 zeros. So how many terms or extrema would it have?
3.
Remember, the degree minus 1 is the maximum number of extrema. So it could have 3, or it could have 1. So as a review detail there, say again, how could it have 1? So one of the things we talked about is they come in pairs. So you can always take away 1. So it's either going to be 3 or it's going to be 1. One way to see that is, so remember how this is y equals x squared, it touches and bounces away? But this could be y equals x to the 4th. Remember how it flattens out and then goes away? So how many turns did it have? Does that make sense? That's how that can happen, is if it's having that higher multiplicity, it comes in pairs. Oh, I'm not saying that one does.
Yeah.
Yeah. I'm just saying, in general, if it's a 4th degree, what kind of number of extrema could it be? It could have 3 or it could have 1. I'm using this as a review for lots of different concepts.
Your stars are interesting.
Yeah? So there we go. So it could have 3 or it could have 1. As a quick reminder from here, the last detail I do want to point out is, because it's 4th degree, what do we know about the end behavior? It'd have to be the same. If it's even degree, it has to be the same. So it has to be up like this, or it has to be down like this. And I will point out, please notice we should not be talking about concavity here. Concavity, just being up or down, is only true for a parabola. This is not quadratic, right? It would look closer to something like this, right? 3 extrema, but notice it has that same end behavior. Anyone know which end behavior would be correct here? The first one or the second one? Say again.
Between those two?
Between these two, because remember, the end behavior has to be the same.
I thought you said it was
Well, so even if it was the 3 extrema, notice how it would have exactly the same end behavior. So when I have even degree, instead of drawing out exactly what it looks like, because I don't know exactly what it looks like, that's even, and I know if the leading coefficient is positive, it's going up like that. If the leading coefficient is negative, it's going down like this, just like a parabola going down. So I can draw a parabola just to make sense out of the end behavior. Anyone know? Think it's top one? Is that because of that 3 up there? Okay? Okay, so let's, as a final detail, if I were to sketch out each of those factors, negative x plus 3, that's a y-intercept of 3 with a slope of negative 1, so that line would look something like this. X minus 4, y-intercept of negative 4 with a slope of 1, so it would look something like this. And x squared minus 4 would be a parabola. We already found the zeros here, and so it would look like this. So let's sketch out what this would look like. So looking to the left of this 0. This factor has positive values, this factor has positive values, and this factor has negative values. What's a positive times a positive times a negative? Negative. So when I actually look to the left here, all of these values are negative leading to here. Oh man, so and I'm just going to look to the right over here for a second. When I look to the right of this 0, so we've got to remember, if I'm trying to sketch, I need to identify those zeros. When I look to the right here, what type of factors or values would the parabola have on the right side here? The parabola's going up, isn't it? So that the parabola would be positive, the line would be, and then this line would be, was a positive times a positive times a negative. So these are all going into the negatives. Oh dang. Here's why. Positive 3, but you see how that's a negative? So a positive 3 times a negative 1 times a positive 1 times a positive 1, that's going to give me negative. That's why it's going down like this. But notice we don't have to stress that detail if we just draw the factors and then we multiply by what's going on. And I check in between my zeros. And I look at each factor. In between these zeros, this line has what types of values? Positive. This parabola has negative. This line has negative. What's a positive times a negative times a negative? Positive. So notice it was negative, it goes through the 0, goes way into the positives, and then comes back down to my 0. Notice, is that a single or a double root? How many factors go through there? So it's only a single, so it should go through. And let's check. Positive times negative. That'd be a negative, so we see how it goes through into the negatives. Then it should go into the positives, and it does. That's what that quartic, or 4th degree, would look like. So we want to note, this review covers a lot of ideas. I know I went through it somewhat quickly, but I also recorded it, and I'm putting it on YouTube. If you know that you need a review on how to identify zeros, if you need a review on end behavior for polynomials, if you need a review on degree, if you need a review on extrema, and a review on how to sketch this function, I just covered all those concepts. That was like over 2 different units worth of, no, that was just 1 unit. But that's a lot of information that can help you long term. Yes, Shania? Nope. Why? Okay.
I mean, it'd be long, like an hour long.
Yeah, but I mean, it depends on how much time we spend in the vertical surfaces, but they've been longer recently because I have been having to do more direct instruction to get through all the content we need to get through. But,
Do other
I-
teachers like comment on?
no. When I teach AP Stats next year, I know I met a teacher at that last workshop I went to who wants to watch the videos to help her teach AP Stats.
Yeah, that's what I was saying, not like to
Yeah.
judge you, but.
No, like that, she already told me that she wants to see that, she wants to watch it, so. What am I gonna say? Or what was I saying? Oh, please use this. Even if you are appearing disinterested right now, guys, this is a review of everything. It is much better to come to tutoring. I can help significantly more in tutoring, but this review is everything that we've talked about within the last unit, except for multiplying, but hopefully we know how to do the multiplying part. Yes, Miracle?
Is your exam here on the 22nd or 23rd?
It's the Monday.
So that's 23rd. Not
Is
26th.
that Tuesday, Friday?
Tuesday, Friday. Tuesday, Friday. Yeah. Yes, ma'am. Good. Quickly, we're about to start. Yes, ma'am.
Wait, next week?
Oh, that's right, you did. Go quickly, ladies. We gotta move quick. All right. We're not making a mass exodus for the bathroom. I'm only letting Jaylen go because she asked earlier. And I told her she had to do the bell ringer. All right. I know, I shouldn't have let Desiree go. No, that was unwise on my part. Should have just started. But we're not all three going at the same time, for sure. So, I don't even think I had the time to update the agenda. But yeah, one thing, Shania, is like, I barely am making it with a baby at home and grading super far behind on, well, actually I'm almost caught up now, but I don't have time to edit videos, I used to. So, what you can easily do though is jump around, right? So the first 20 minutes of today's lesson is that review. If that's all you need is that review, just watch those 20 minutes.
What did mainly be our favorite?
I've mostly recorded in this class because I can, so like when I record it splits the video up into multiple pieces and I put those pieces together to make it one single video. And then I upload during third block. Huh?
And when I was well.
Well, you're more respectful than my fourth block. Or third block, I mean.
Yeah. You don't have, I was gonna say you don't have.
I don't have fourth block. Yes, ma'am.
That's for sure.
Okay. Okay. Oh. Hey, he won't be in my class.
Oh, it's sure I mean the turn. I wrote it down.
Alright,
April 28th.
so, mathematics, it's a beautiful endeavor of studying what ideas? Patterns and relationships. So, let's get into that. Let's look at the idea of what is an inverse function. Reflection across y equals x, causing inputs and outputs to transpose. What is the number e? Close. Okay, so e is the natural base, named after what mathematician? Leonard Euler. And it is approximately not 2.17, but 2.718. And you go to 1.828, but at least 2.718. That's what e is approximately. So you just mixed up that 1 and 7. So that is the number e. I will remind you, because this is where we are picking up today. What is a logarithm? Today is, yes, 17. It is
A number,
Exponent.
an exponent to which a given base must be raised in order to produce a number of y.
Yes, Amy. We're about to go over it.
B.
Okay, ma'am. Go quickly. So, logarithm is an exponent.
Yes.
So what is the logarithm here? What is log base 3 of 9? Why is that? There we go. The best way to understand a logarithm is to think through it as the exponential, right? 3 to what power is equal to 9? Tomorrow on our understanding check, be aware, 1, I'm going to give you an exponential function. I'm going to ask you to graph the inverse of that exponential function. I'm going to ask you for domain and range of both. I'm going to ask you for the intercepts of both. I'm going to ask you for in behavior of both. The stuff that we've done for the last 2 days straight. So
Nice.
make sure you're prepared for that.
How many questions?
I don't remember that off the top of my head. And I will ask you to evaluate some logarithms. So please be aware, there is going to be no calculator because I've already given you the graph. There is no need for a calculator. I need you to think through some things. And if you can at least tell me what you know about a logarithm, then you will be okay. The majority of the assessment is not on the logarithms, but at least think through what you know with it. Yep, didn't update that at all. So, here we are in lesson 3, logarithms. We got past all of this in here, thank goodness in this class. We are behind in the others, but that's what I'm trying to get to. Nope, we still got learning. Okay, so this is page, that doesn't say what page it is. Thank you, sir.
What page?
134. By the way, I do want to point something out. Again, I already mentioned that I'm trying to find your, I'll figure out where the other ACT scores came from. But in glancing through these, and it may be that some of y'all just asked, no, you should get a paper copy, I don't know. In glancing through these, something I want you to be aware of is if you actually look at your scores again, I think across the board, except for maybe for one student, you know what the highest score was? Math.
Math.
No. Your high, look, everyone who got their paper back, if you look at it, your highest score was the math portion.
Are you proud?
I'm happy for y'all, but I am proud of that for y'all. But also, I do want you to understand, like, there was quite a few of us, more than I've ever had before, who made on the survey, didn't think that they were thinking mathematically better than they had before. And that, I hate that, but that is an interesting detail that was still your highest score. So, while it's been tough, while it's been a struggle, please understand, like, what I'm doing is designed to be for your best, each and every single one of you, because I do care about you. There's a reason why that was the highest score across the board. Say again, Hayden? So, yep. So, let's look at this. Function, a basic exponential. Y equals, did I already have you write b to the x? Yes. And yes, Hayden, I did already see yours, so I will count for that in a second. So y equals b to the x. This basic logarithmic here would be, I should probably use f of x, let's do that. Okay, f of x equals b to the x. For a basic logarithmic, how would I write this then? Be careful with that language. Of x, right? That logarithm is read as log base b of x. It's not an exponent, right? What the logarithm equals is an exponent. Trying to remember what I was going to say there. Oh, tomorrow, one of the things I am going to ask you to do is actually I've given you a graph and an equation of an exponential. I'm going to ask you to identify what the inverse equation is. And so we'll go over the understand check immediately so that we'll get that. But this is technically all the information you'll need to be able to get that. We need to notice that the logarithm has the same base as the exponential, and then you'll be good. Here are examples of the graphs. Do notice, if I gave you the exponential graph, how could you get the inverse logarithmic graph? What's the little line? So 1, I could reflect across y equals x, and even easier, Miracle, what did you say? Transpose the
Y.
and x, there we go. The inputs and the outputs. Notice negative 1, 1/2 became 1, 2 became 2, 4 became, and then even here 0, 1 became 1, 0. So if I give you an exponential function, you can easily get the inverse function from that. Okay? As inputs and outputs are transposing. And we want to keep in mind, so what does this logarithm mean? Well, if I take log base 2 of 1/2, that's my input, what's the exponent? Well, so remember, the 1/2 is my input. Oh, it might be hard to see over there. -1 is my output because 2 to the -1 is 1/2. Okay, so we have our graphs there. We should already have these things filled out. And we've done a lot of practice with this. And again, this will be on your assessment tomorrow. So if you have questions as I go through these, you need to ask them. Domain of the exponential, what's that domain? There's my domain. Don't forget, you definitely want to justify these things. Evidence of understanding. Just writing -infinity to infinity could be a great guess. It doesn't tell me you understand what domain is. It's the set of all inputs, or x values. You can make the note that that's my lowest x value, and that's my highest x value. What's the range for the exponential? And so I'm going to pause and let you ask questions if you have them.
Why is it 0?
Okay? So what does range refer to, Eliza?
The set of y values.
Okay? So I want you to think about it. Where do you see the minimum y value for my exponential up here?
Right there in blue.
For that blue, right? See how it stops and never gets to here? That's the x-axis. What's the y value on the x-axis? Think about your x-intercepts. What does every x-intercept have in common? The y value is? So what's my lowest y value? So it's 0, my minimum y, to my maximum y. That's it. Okay? Any more questions about that domain and range? Look it up.
Which one is the
Well, try to ask a question, then you can. Yes, ma'am.
the line for the y-axis?
The line for the y-axis? So if the line for the equation for the x-axis is y equals 0, what would make sense for the y-axis?
The orange one.
Huh?
The orange one.
Can you ask your question again? I think I'm missing the detail.
What did I just say?
I think you asked what, I thought you asked what is the equation for the y-axis. Is that not it?
No. I said which line is the x-axis?
Oh, this black line right here is my x-axis,
No,
right?
I'm saying like for your graph. Like the line on this plotted on the graph.
So this exponential, the blue is approaching the x-axis. But that's not what the x-axis is.
Okay.
I'm trying to think, if if you can figure out a different way to ask that question, I'll try to rephrase my answer so I can explain it better.
Okay.
But like, this black line is the x-axis.
Yeah, I know that. I was saying like, you know, like the domain is x values.
Right. So like if I look at this blue function, you see how this goes to the left for forever? So the lowest x was -infinity. This up here has an understood arrows, meaning it goes up and to the right, so it goes to the right for forever. So the maximum x is positive infinity.
Okay.
But like when I talk about the y stops and doesn't even get to the x-axis, so the minimum y is 0. And then it goes up for forever. Okay? Intercepts. What intercept? Oh, actually pausing there. Knowing that domain and range, what should I know immediately about my inverse function? Let's think about that language a little bit, because the opposite could mean infinity to -infinity, like just taking the opposite of that domain. Is that what we mean? So the domain and range switch, right?
So it's gonna be infinity and 0.
Zero.
So it's going to be 0.
And then negative
Two.
infinity.
So remember, pause infinity. And so notice, we can check. Look here at this graph. What is the lowest or minimum x value for this graph? The lowest x. Does it go?
Zero.
Does it ever go to the left of the y-axis? So what's the minimum x? 0. And then it keeps going to the right for forever. So what's the maximum x? Infinity. Yes, ma'am?
No, I was gonna X, why you checked 0, but I see it.
Okay. So yeah, remember Jalen, for the inverses, the domain and range switch. So that's one detail, and the second detail is if I look at my minimum x, it never goes past the y-axis, so the x value there is 0. So this should be my range. What is my minimum y value for this function? It's going down and down and down and down to what? Negative infinity. My minimum y. And what's the maximum y? It's going up for forever. To positive infinity. Okay? Intercepts. Well, first off, questions, comments, concerns. All right. Yes. Intercepts. What do we have? So y-intercept here for the original function, and that y-intercept is 0, 1. So what do I immediately know about the inverse function? It's going to be an x-intercept. So Marshall, why is all of this happening? Why is the domain and range switching? Why is that y-intercept becoming an x-intercept and 0, 1 is becoming 1, 0?
Because the functions change.
Yeah, but how does it change to make that specific change?
How does what change?
Like what is changing about this function when I get the inverse that a y-intercept is becoming an x-intercept, that the domain is becoming the range, and this range is becoming the domain? Why is all that happening? The inputs and outputs transpose. This is a beautiful pattern that shows up time and time and time again with those inverse functions, that the inputs and outputs transpose.
Is that always for the y-intercept and the x-intercept?
For the inverses, yes. Because remember, if I'm talking about an inverse, the inputs and outputs transpose. So that 0, 1 becomes a 1, 0, which is an x-intercept. Okay? Asymptotes. What line does my exponential function approach? What were you going to say? The x what? Which was the equation on the x-axis? Y equals 0. If all you know is the x-axis, that is evidence of understanding, 100%. There's the x-axis. But what we do want to recognize is that the equation for the x-axis is y equals 0. Because what is the y value of every point on the x-axis? The y value is 0. So to indicate that every y is 0, we write the equation y equals 0.
So that's always, or does it like changes with the graph?
It can change with the graph because we can have transformations called translations, shifting things up and down. So for example, let's say that I have a new exponential function where I actually translate it up 2 units, and it looks like this now. What would be my asymptote at this point? Look again. See how it's approaching this line? What's that y value? So y, the asymptote here would be y equals 2.
So it's going to be based off like what it touches on the y-axis.
Well, it's going to be what it approaches, because that's something you want to be careful about. It never actually gets to this y value, it's approaching it. Yeah. And so that is something that is possible on the graph tomorrow to see if you really understand what an asymptote is. I could have a shift like this. Okay? And I would point out if this is what the asymptote is here, this inverse would look something like this, and what would the asymptote be for this logarithmic one? X equals 2. So that's something to keep in mind. Alright, so, but for the function we have, what's the asymptote for the logarithm? So the y-axis, and once again, inputs and outputs transpose, so x is equal to 0. Now, in behavior is something that takes practice, 100%. But how many in behaviors are there always? So we need the left hand and the right hand. So if I'm looking at what is x approaching on the left hand side for an exponential function? And as x goes to the left towards negative infinity, what's my y going towards? Notice, does it ever go up? Does it ever continue going down to negative infinity? It goes towards 0, that horizontal asymptote. As x goes to negative infinity, the y goes towards that asymptote right there.
Stop.
Sometimes, but it's a line that the function approaches. So remember I showed this example just a second ago. In this case, you see how it's approaching this line? That line is y equals 2. So it's that line that the function approaches. And I will never ask you to give me the asymptote without a graph at this point. Like you will have to do that in pre-cal, but not in Algebra 2. Okay, in a pre-cal class you would have to do that. No? Not happening? Okay. What's the right hand in behavior? As x goes towards infinity, what is y going towards? Infinity. So that's for the exponential function. What about for the logarithmic function? Left hand side. What is x approaching? So it's approaching that y-axis, an x value of 0. And as x goes towards 0, y goes towards? Okay? So Phoebe, why is this the end behavior for the left-hand side?
Because they swap.
What swap?
Or the x and y of everything. Swap.
So the x and the y
Is swap.
swap, right? We're talking about an inverse. So when I look at the left-hand side, that x becomes the y, and the y becomes the x. We cannot forget that with inverses. We can also, again, see it, right? So we want to know that detail at the inverse, but we also want to be able to look at the graph and say, what's my x going towards? It's going towards the y-axis, or an x value of 0. That also matches the asymptote. Right hand, as x goes towards, the right-hand side is infinity, y is going towards infinity. Yes, ma'am?
So just write all of that in the word block.
Hopefully, I think there's a little bit of space at the bottom, because yeah, it's impossible to fit all that in there. So I might just go below it, but Jacoby and everyone, make sure we remember how many in behaviors are there? 2 for each function. Every function has a left hand in behavior and a right hand in behavior. We are jumping some, so I'm about to show a summary of what we are covering. If I were you, would probably write this down on a sheet of paper to pay attention to what to study for your test and for the understanding check. So this lesson, we're still applying, but that was on the old understanding check. It will be on the test. This is what we've been covering the last couple of days. This will definitely be on the new understanding check. And this is what we just wrapped up, Module 3, Topic 2, Lesson 3, right? And what we're about to do is, and that covers the inverse of an exponential as a logarithmic function, the features. What we're about to do is focus on a logarithmic operation, so how to take a logarithm of a number, and we will get past this, but that's at least what we'll do. So be aware of that. Yes, ma'am? You didn't get one of those yesterday? Here you go. Oh. Why did you get in there like that? Miracle just loves abusing hate. Okay. Does anybody want to ask any final questions before we wrap up this lesson? Say again. Understanding check. So a check on understanding. It'll be that, but what we're about to do is evaluate logarithms as well, which will be a small part of it. So it's not anything beyond what we've already done, but it's going to help us practice evaluating logarithms. Okay. So this is on page 171. So as I said, we're having a bit of a jump because we don't. I'm just having to pick the most important parts, essentially. So page 171. This is focusing on evaluating logarithms and solving logarithmic equations. And so, we're talking about all the pieces of the puzzle. So logarithmic expressions, so learning how to evaluate them, how to solve logarithmic equations, and we've got a good 40 minutes to do this. The getting started here is what we want to look at this point. All we have is you're either given an exponential equation and you need to convert it to a logarithmic equation, or you're given the logarithmic equation, you need to convert it to the exponential. And we're going to work on this within our small groups in a second, but I do want to do two of these with us, or with you. If 12 squared is equal to 144, which it is, what is the logarithmic version of that? So whatever the base of the exponential is, that's the base of my logarithm. So remember, what was my output is going to become mine. And also, a big thing to remember is, what is a logarithm equal? It equals an exponent. So my exponent is what it needs to equal. Right? So a logarithm is equal to an exponent. Whenever we evaluate a logarithm, we're getting an exponent. So we need that exponent to be what the logarithm equals.
So, the logarithm is going to be on the 6, right?
Say that one more time.
Is this going to be on the 6?
Be able to convert back and forth? Yeah.
But did you say we couldn't use a calculator?
So there, on the test, there will be a calculator and non-calculator portion. And so some logarithms, if I'm asking you to evaluate them, yes, you'll have a calculator. But one thing to remember is, with a logarithm, the calculator will just give you the answer. So like, I have to play around with it, see how I'm going to ask those questions. But if I give you this equation, it's just a matter of rewriting it like this. And that's more of what I'll focus on. 171. So if in the second one on page 171, if log base 16 of 4 equals 1/2, how would I write that as an exponential?
So that's the 4 term, or to the same? Whatever it says.
So remember, log, just because you said 12, what's my base? Okay, so my base is 16. What's the exponent? So remember, a logarithm is equal to an exponent, right? So 16 to the 1/2 is equal to 4. And this ties into something we got to actually talk about yesterday that I didn't get to talk about with the other classes yet. How in the world does 16 to the 1/2 equal 4? That's something with a square root. Remember, what the denominator is, that's the root. And if it's a square root, we don't write anything, but it's understood 2. And then that's 16 to the 1st. So what is the square root of 16? That's 4. That's what that's saying, right? 16 to the 1/2 should really be read as the square root of 16. So within our groups, I do want us to work together to write these exponential equations as logarithmic and my logarithmic as exponential. The one thing that might trip us up is right here. When we say ln of 20.086 equals n, this is something I covered very quickly at the end of class. What logarithm is ln? What base is that? It's called the natural log. Well, what number is known as the natural base? So 10 is the common base, natural is e. So when you see that ln for the natural log, and we're very close on that, all we have to remember is that that's a base e. So let's work within our small groups. Let's get as many of these equations written within the next, let's say, 4 minutes, and then we'll come back together for a whole class discussion about the ones that tripped us up the most. Say again. Well, what's the exponent? So then what's it equal to? There you go. Okay.
Which one you doing? You doing one after this? 10, 5.
Don't forget, it's more interesting when we talk with people. It's way more busy or boring when we don't. Yes, ma'am.
Yeah.
That is one thing I will definitely have you do. So what are we working on?
What are you working on?
Okay, there's a difference between asking the question, what are we working on, and how are you making sense out of this? We should know what we're working on.
Well, you know what I mean, Mr. Kenny.
What you mean is you weren't paying attention when I gave instructions?
I was. I just.
You didn't even write down the 2 problems we did as a whole class.
I don't want to write it down when I get finished.
I've been done for over a minute now.
I like right now.
Desiree, do you have any questions, or are they making sense so far? Okay. So, go ahead. Okay. So we'll talk about those in a second. One thing I do want to point out is you already have the logarithm here, so we don't need a logarithm here, right? You need the exponential. So think about what would the base of the exponential be. Okay, so base e is the exponent for e 20.086. Well, why don't you type e to the 20.086 and see if it's equal to that 3. And so you have the e right there. Does that equal this 3? So remember, what is a logarithm? A logarithm is equal to an... It is the y for graphing, but the logarithm is equal to an exponent. What's your exponent? So it should be e to the... Type in e to the 3rd on that calculator. Did that give you that 20.086?
You did.
Okay. One thing I need you to be careful about on notation is right here, actually. When you do a logarithm, your base is a subscript. It's not in line with the log. The argument is in line with the log. So log base 10 of 10,000 is equal to 5. That's the proper notation. You're making that exponent, right? That's closer to it. But even make that below, right, at the bottom part of that g, and then the argument needs to be in line with your logarithm. Okay? So one thing I want to point out is if you are understanding how to convert from a logarithm to an exponential using your base and using your exponent, then you can do this, right? Find your base, find your exponent. If you recognize your base and your exponent here, even though there's a variable, we can write it as a logarithm. So think about your base, think about your exponent, work on that together.
What is we're gonna work together?
Z, you actually got to work, dude.
That's what I just said.
How's it going? Questions, or are we feeling okay?
Alright, so what you did so far?
are you talking about? That one. So if we do base E, so you said E equals 3? Okay, so E to the third is at approximately 20.086. It's close enough. 20.0855 would round up to 20.086. So when we say Ln like this, that's known as the natural log. And natural log is log base E of 20.086. Okay. So remember, when we talk about natural log, that is base. So the base is right, and it's raised to the third. Yes, ladies. Sorry, screw. We're about to get started, so. Okay, so let's go over it. Okay. All right. So, a couple of things to look at here. The natural log again is giving us some trouble, but when I look here, 10 to the 5th is equal to 100,000, right? Which I think I miswrote that on someone's. I think I wrote 10,000, so check yours. I might have written 10,000 down, not 100,000. But that's exponential. I need a what for the inverse? Logarithm. So Jalen, what would be the base of this logarithm based on the exponential? Log base 10 of 100,000. That's it. That's all it is. The base of my logarithm is the base of the exponential. The exponent is my output, so this 100,000 is my argument or input. Okay? I will point this out though, you can actually write this slightly differently. Does anyone remember the name of the log base 10? It's the common base or the common logarithm. That's the natural one. So we got to keep in mind common versus natural. Common logarithm is the one where you do not have to write the base. You could have just said this. Okay? Those two things are equivalent to each other. So I'm going to use the 3 lines to show equivalent. Could you still write that base 10? Yes. Just be aware, mathematicians and scientists will not write that base 10 because it's a common logarithm, it's understood. Okay? It's a common logarithm, it's understood. Just like with the square root of x, what's the understood index right here? Remember, it's a square root, right? So it's the inverse of a quadratic. And so that's the same kind of idea. Don't forget, with a natural log, it is understood to be log base e. So what's the base of my exponential? E. What's the exponent? 3. And is that approximately 20.086? With rounding, the answer is yeah, but check it. So don't forget, whatever a logarithm is, we want to think about the exponential to make sense out of it. Ma'am? Broke your what? Broke your toe? Wow. That does not sound like fun. No. Okay, so here are the answers. Which of these do we need to discuss or talk about so that you can improve your understanding? Okay, so this one again. And the 2 to the 8.
And this one is the first.
This one?
2 to the 3rd.
2/3 to the 3rd? Okay. So, just remember, Jamarcus, if I see that ln, what that ln stands for is the natural log, which has the natural base e. And if you understand what your base is, the base to that exponent is equal to the argument. So you just have to recognize that if I see ln, base e. That's it. If I see a log without a base written, it's understood to be base 10. Okay? Yes, Jalen?
So on the second to last one, do we just leave it at x instead of 2?
So you can rewrite it as a 2. But as it is right now, right, log base 6 of 36 is equal to x. So that's actually what we're about to talk about is how can I use this to solve an equation, okay? What is log base 6 of 36? What exponent goes on 6 to give me 36? 2. So we can evaluate it to answer the question, okay? So, Eliza, you're asking about 2/3 to the third? So what's my base for this exponential? So log base 2/3. Remember, a logarithm has to equal the exponent. So what's my argument right here?
8
Say that one more time.
8
8 divided by 27. That's it. That's all I did. Someone asked for the 2 to the 8th? So what was giving you trouble about that one, Grace? Okay, good. And so I will point out, this is another instance of being able to solve a logarithm. I don't know log base 2 of x equals 8 off the top of my head, but if I rewrite it as an exponential, can I figure out what x is now? Yeah, somewhere around 128, 256, I think? Yes, Jayla.
On the 9 over 2/3, how did you get 2/3 when it said 3 halves?
I miswrote it. Thank you. That makes more sense. I will point out, with that 9 to the 3 halves, let's talk about why does it equal 27. What does this denominator 2 tell me about? What am I really doing to that 9? I'm taking the what? So when I have a fraction for an exponent, remember that's a root. Which root? Hey guys, we gotta learn this. Which root would this be? Well, first off, what symbol do I draw for a root? So a radical. Okay. Which root would it be? The square root, the second root, which is understood to be the square root. So I don't actually have to write it. Square root of 9, and what's happening to the square root of 9 is being cubed. What's the square root of 9? 3. What's 3 cubed?
27.
That's why 9 to the 3 halves is 27. Okay. Questions? Concerns? How do we feel about converting? Not necessarily knowing all the values, but at least converting back and forth. What I will point out, it is the most important idea, is you have to identify what first? The base. It is all about the base. Okay? It's all about that base. And then identifying, I know. I said it and I was feeling whatever. Alright, base and then the exponent. We gotta identify those things and then it's nice from there. Okay? Notice here in activity 1.1, it's talking about using this notation, just identifying the base, the exponent, and the argument. That's exactly what we've been doing this whole time. And not to scare you or anything like that, but what do we mean by a logarithmic equation? Well, the logarithm is an exponent. When we evaluate a logarithm, it's an exponent. But just think about those two words. A logarithmic equation, that'd be a logarithmic function. So let's look at this. What would we call that? Quadratic. It is a standard form of quadratic, but it's a quadratic what? Equation. Well, it's an equation with a quadratic, right? So what do I mean by a logarithmic equation? That's it. Yeah, don't make it complicated. But we need to know that mathematical vocabulary. We have to be able to talk about these things. So, notice, it's defined right there. All a logarithmic equation is an equation with a logarithm. Make sure you note that, you star it, you highlight it. We are talking about logarithmic equations. So, for the sake of time, let's do one of these together, I guess. I'm going to have you do B and C. So when I look at 49, 2, and 7, I need a logarithm of some base, or logarithm base of an argument equal to an exponent. Does anybody see, and I might even start with this, does anybody see an exponential equation that I could create with 49, 2, and 7? 7 squared is equal to? So then what would be the logarithmic version of that? So log base 7 of 49 equals 2. Remember, the equals the exponent. So we're just trying to create a logarithmic equation. So try B and C with each other. We'll come back together in just a second to discuss this. Come on, you cannot be upset about grades and have your head down like this. One thing to be careful about. This 49 you're almost writing as an exponent. The 49 needs to be in line with the logarithm. The 7 is a subscript at the bottom. And then the 49 is the logarithm. So, see how those are literally in line with each other? Like if there's a line on the piece of paper, see how they match? Okay.
Yeah.
So that's something you want to think about when writing your logarithms. Some other thing I want to say to you right here, if we have a line right here, okay, like a line paper, we want to write a log. The 4 needs to be a subscript for the base, and then this 4 needs to be in line. It doesn't look like an exponent, it looks like it's in line with that log. Does that make sense? Because I looked at that and I was like, why are you doing 4 to the 4th? And it's just because of the way it looks, so be careful with that. How could you check? So, let's think about it. What you're telling me for an exponential is that 1 divided by 216 raised to what power? So remember, it's a logarithm. A logarithm, right. Does that equal -3? So let's think about it again. Good thoughts, but let's see how we could rearrange those things. Okay. So Jamarcus, what are y'all thinking for B?
Log 6.
So log base 6.
-3 equals 1 over 216.
1 divided by 216. Okay, so can you tell me why y'all are thinking that one? You got a different one? What'd you get?
Log 6, 1 over 216.
Yeah, that's fine.
Equals -3.
So, I'm going to come back to what you just said in a second. Did you type this into the calculator? Oh, you just typed the equation in? Okay, so let's look at this. So remember, in Jamarcus, if we're writing this logarithmic equation, you're saying for the exponential you have base what? And what would the exponent be?
-3. Oh.
Is that what you're saying here though? So you said the exponent is -3, but remember, what is a logarithm equal to? Well, the logarithm equals an exponent. What a logarithm is an exponent. So it needs to be log base 6 of 1 divided by 216 equals the exponent -3. So whatever the exponent is, that's what the logarithm equals. Also remember, what was my output, so it should be 6 to the negative 3 equals 1 by 216. What was my output needs to become the input. And what was my input needs to become the, do you see that now?
Yeah.
And this is why I like to write that exponential first. That's important information. Okay, C, what base for my logarithm? What for my argument? Equals an exponent of? If you went ahead and tried it, the last one is log base 4 of 256 is equal to 4. Yes, ma'am. There will be, not where I give you 3 numbers like this and you create your own equation, but creating an equation like this is helping us talk through what is a logarithm, and I will be asking questions for you to evaluate a logarithm and explain what a logarithm is.
So when you want to ask like what it is, you want us to explain like what's an example of this?
You can, yeah.
Like when it has like those arguments.
So you can write it out like that, but you can also just write out a sentence, a base raised to an exponent is equal to the argument, and vice versa. Yes, Eliza?
Can you explain,
Yes. So what were you thinking? Log base 4 of?
I didn't do,
Okay. Well, so remember, if you think about the exponential, 4 raised to the 4th is equal to 256. So I straight up, guys, logarithms are hard to think about in my head without thinking about the exponential. I always create that exponential to make sense of what the logarithm is. Because I know a logarithm equals an exponent, and so I write that exponential to make sense out of it.
and then you did, C plus 4 to the first bracket.
Correct. Yep. And notice that logic is what I'll be looking for on our assessment. 4 to the first is equal to 4. Okay?
I feel like that's kind of
You heard.
I mean, it's a pattern. Yeah. I will say I'm glossing over, and I have skipped the more complicated aspects of it because of compressed time frame. But yes, this is what we're used to in most of our classes, where we skip over the hard stuff. Yes, Jalen. Yes, ma'am. Yeah. All right. Really quickly, so I want to point this out. This is how we're going to be solving exponentials. If I have log base 4 of y is equal to 3, which this is on the next page, 174. If I have log base 4 of y is equal to 3, then 4 to what power? The third is equal to? Well, it's equal to y. Now can I figure out what y is? Yes. And they ask, okay, so justify the last step. If 4 cubed equals y, why does y equal 64? Well, because 4 times 4 times 4 is 64. And so it's just rewriting the logarithm as an exponential. If log base 4 of 64 is equal to x, 4 to what power? X is equal to? And now we just have to figure out what that exponent is. So 4 to what power is 64? The third. That's what makes the equation true. And so you didn't have to convert this to an exponential, but when I ask log base 4 of 64 equals x, what is x? Well, log base 4 of 64 is equal to 3. That's the exponent. Okay? And then I won't make you solve for an unknown base.
Yay.
I will. Let's talk about it at least a little bit. So one thing I do want to point out here is this. Traditionally, what have we always used to solve an equation? Say again. Well, we need a variable, right, to be able to solve, but like to actually solve the equation, what have I used? Starts with an I. Inverses, right? With properties of equality. So I want you to look at this and think about this equation right here. Log base 4 of y equals 3. What's the inverse of a logarithm? Remember how a logarithm was the inverse of an exponential. So the inverse of a logarithm is an exponential. The way that we would actually show that inverse is this. This would become my exponent. So this would be 4 raised to this power is equal to 4 raised to this power. Notice I'm using an inverse. And what do inverses do? Be careful with that language. We don't want to use the word opposite. Now, when we talk about inverse functions, the inputs and outputs transpose, right? But when I talk about solving an equation, what do inverses do? Say what? Say it louder. You say reflect? But that's again when we're talking about the function. Guys, if I have x squared equals 16, what am I going to do to solve that equation? Because the square root and the square cancel, right? When solving an equation, what do inverses do? They cancel. Because these are inverses, those would cancel. And what would I be left with? See how that's the same exact thing that we got over here. My point is simply that we can still use inverses to solve our equations. And I bring that up for this third one here, which is a little bit more complicated on the surface. Log base b of 64 equals 3. We can just convert to an exponential, or what's the inverse of a logarithm? Exponential. So this is going to become my exponent with what base? It needs to be the same as the base of the logarithm to cancel. And what do I do to one side of the equation? So the b and the log canceled, and I'm left with 64 equals b. I bring this up because how would I then solve this equation? Which root? So I just wanted to remind you that math is the study of patterns and relationships. There's always that relationship of using inverses at some point. And so we can solve this equation. The cube root cancels out the cube, and the cube root of 64 is 4. So you can still solve that equation. We only have 3 minutes. Move to number 3. So, oh yeah, it's right there on the next page. So moving to number 3, I want you to work. By the way, this went over here. Yeah. Looking at number 3, I'm just going to give you 3 or 4 minutes to work with each other to solve as many of these equations as possible. Figure out what your variables are. We'll come back and have a whole class conversation for the last few minutes of class. So I'll be coming around trying to answer questions as you work. You know, all of this is on the next page, right? All that's written, well, the 741, I know, but all of that stuff on the right hand side that we just talked through goes right here. This was the page I had up there. Now, all of that went over here. See? Pay attention. So talk a little bit, try to figure out what some of those equations are. Do you have any idea how to figure out what n is for a? So what I would remind you of is what is a logarithm equal to? So what exponent do I need for this? So 8 to the 4th is equal to 64? So think about that some more. Okay. Have we chosen with each other? Okay. we're looking at these.
Oh,
You are not wrong, but those are the ones we're looking at. So remember, you're just typing into the calculator, right? What we need to think about is how are we figuring this out, right? So why is log? So that's what you need to be thinking about, right? So what is the exponent? Helps you do that so you can focus on what we're learning right now. Yeah.
So log, I think you just put 10.
Okay, let's talk about it. Yeah. So hopefully we have at least A done. Let's look at A. So do not forget, what is a logarithm? An exponent. We can't forget that. So when I look at this, you can rewrite this as an exponential, right? 8 to the n is equal to 64. You didn't have to, though. What is that n right there? It has to be 2. Because 8 squared is equal to 64. Don't just type these in a calculator. Let's think through it. Because this helps you solve for b. So b is a little bit harder, though, isn't it?
Yeah.
But what's the base for b? It's unknown, so it's n. Raised to what power?
1 divided by 16.
What's my exponent? Remember that logarithm equals an exponent. Equals what? 1 divided by 16. So one thing I would point out here, there's actually a couple ways to do this one. The easiest to remember is this. What does a negative exponent mean? To repeatedly what? Not subtract, to what? Divide. When I see a negative exponent, right? A positive exponent is repeated multiplication. A negative exponent is repeated division. So how many times am I dividing by n?
2.
So I'm dividing by n twice, and it's equal to 1 divided by 16. So what would n have to equal to make this equation true? What squared gives me 16? 4. Okay. N is just equal to 4. And so we want to think through, okay, rewrite that as an exponential. And that'll help you out.
So,
Yes, ma'am. D.
how would you do that with it not being like a number?
I know. Does anyone remember what base it's understood to be? When it's just log, no base written, it's understood to be common base, which is base 10. So I see this, I know, hey, that's 10 to what power? To the negative third is equal to n. And we just talked about it. A negative exponent indicates repeated division. So that's 1 divided by, how many 10s am I multiplying? How many 10s in the denominator? 3. So 1 divided by 1,000 is equal to n. So, when you hear people complain about logarithms, be like, yo, logarithms ain't that bad, they're just some exponents. Don't make them complicated. We will start tomorrow with our understanding check, and we will do this always, sometimes never, to talk about some values, and just get some more practice with those equations. So we're going to do our understanding check tomorrow to start. And this is all we have gotten through. So just these 3 lessons on the understanding check. It's a lot of lesson 3 and a lot of lesson 1. Please, you need to finish up any final workspaces. I know some of us are looking to do a retest today. Make sure you don't forget if your parent signed you up for one. And I think that's all I got. Yeah, it's on there. I just haven't. Huh? No, just the most recent one. Now, if you have one particular test that's really bringing down your grade and you learn, and
Well, you went a little too far with that one.
Was it the solving quadratic equations?